In this video, I want to give a quick introduction to groundwater flow and Darcy's Law. So this is Darcy's Law. You've seen this equation before, but maybe not in this form. So in this form here, Darcy's Law is expressing the discharge due to groundwater. So Q is the symbol that you know and love. It stands for a discharge here with the units of volume per time. So for example, gallons per hour, for example. K is the hydraulic conductivity, and it reflects the ease with which water can flow through the porous medium. A here is the cross-sectional area. So this is something that might be different here. This is the cross-sectional area, and I'll explain what I mean by that in a second. And here, of course, this is the gradient of the head, of the hydraulic head. And I can write that, remember, as the change in the head. This is the change in the head divided by the change in the distance. Delta S is the distance over which groundwater flows. Distance of flow. So, for example, let's say I have groundwater that's flowing through a tube that I've filled with sand. So this tube here is full of sand and it's saturated with water. I measure the head at the beginning of the tube and at the end of the tube using little piezometers here. The head difference here is the head difference that drives the flow, and the distance between the 2 points is equal to delta S. So delta H over delta S, that's the hydraulic gradient that's going to drive the flow. And as this happens, then water will flow through this tube. Let me just show you what I mean here. So groundwater is going to flow out like this in this direction. This is my groundwater flow Q. And the cross-sectional area here that I reference here is this area here. It's the area through which the groundwater is flowing. Larger the cross-sectional area, the larger the discharge Q. So this expression then describes the way in which the flow of groundwater results in a volume flow of water. Sometimes we define something called the specific discharge with symbol little q, which is equal to big Q divided by the area. So if you think about big Q, that's going to have for the dimensions, remember, volume per time, the area. When we divide the volume by the area, that means that little q will have the dimensions of length per time. So the specific discharge, little q, has the dimensions of length per time, and we can write Darcy's law. Alternatively, I'll write it over here, is the specific discharge equals minus k times the hydraulic gradient, or equals minus k times the change in head divided by the change in distance. Since the hydraulic gradient, you might remember, these are both changes in length, so this thing is dimensionless. That means that k and q will have the same dimensions, right? And both k and q, specific discharge, have the dimensions of length per time. They are commonly described as either feet per day is the most common unit, or meters per day if we want to use the metric system. So here I've just rewritten these two forms of Darcy's law in terms of the Q's. And when do we use the Q forms of Darcy's law? Well, we use it whenever we're interested in how much water is flowing. For example, if we're interested in the amount of water provided by an irrigation well, then the form of Darcy's law we would use would be one of these Q versions of Darcy's law. Now there's one other version of Darcy's law we use when we're interested in how fast actual molecules are moving. So let's presume we have a field area here that I've outlined in white, and we spill something in the ground right over here, and we're interested, the groundwater is carrying it away in this direction, and we're interested, well, how long is it going to take for it to get over there? And for this, we need to know the actual velocity of water molecules. And for that version of Darcy's law, we use a slightly different idea, and that is we introduce something called the interstitial velocity. This is called, I'll write this down, interstitial velocity, and it is the velocity of a water molecule. It is defined as, we can show that the interstitial velocity is equal to the specific discharge, little q, divided by n, where, remember this, that n here is the porosity. And remember too that this is dimensionless. So that means that Q and the interstitial velocity are going to have the same dimensions, which should make sense, right? Because Q has the dimensions of length per time. That's kind of a velocity dimension, and so should then the interstitial velocity have dimensions of length per time. So using this idea, we can say another third version of Darcy's law that we would use when we're interested in how fast a contaminant, for example, might move as it's carried by the groundwater system. We would say that the interstitial velocity of the groundwater is equal to minus Q over N. So that is equal to minus K over N times the hydraulic gradient delta H over delta S. So we have three versions of Darcy's law here. We use them in different contexts. This is our interstitial velocity version when we're interested in how fast a contaminant is moving, and these are our two Q versions when we're interested in the volume of water that's being moved, and we're interested in water supply problems, such as from a well that's supplying water for potable purposes or for irrigation or for whatever reason. And this is the Darcy's law that we then solve to get numbers that describe how quickly groundwater flows.